So where do we begin? Well, really in the 4th century BC with Aristotle and his theory of projectile motion. And for Aristotle, the idea was that if you fired something, it went in a straight line until it sort of stopped moving, and then it just dropped down. Now, I'm sure most of you will have seen a projectile moving and knowing that isn't quite what happens. But actually, from the point of view of people firing from cannons and so on, really they were at the beginning. I mean, cannons really came into existence around early 14th century and so on. They were firing at stationary objects. So they didn't have tanks and things coming towards them or anything. They were wanting to kind of lob their cannonballs, into a castle keep or something like that. And so actually, as long as it kind of went far enough and it dropped down, then that was good enough. And we can see in this diagram here, which is from 1561, exactly that sort of motion. So you have the cannonball goes up and then it comes straight down. But after Aristotle, really the first person to try and do some analysis of the motion of a projectile, particularly with reference to ballistics, was an Italian mathematician, Niccolò Fontana, better known as Tartaglia, which means the Stammerer. He was, as a child, I think he was age when he was about 12, in the Italian wars. He was very badly wounded by a French soldier, in fact left for dead, but his mother nursed him back to health, but he was badly scarred, and that's apparently why he always had this kind of rather voluminous beard. But most people if they know about Tartaglia at all, they know about him for solving cubic equations. And that's a whole story, and we could have a whole meeting on that, but we're not going to go there. But the reason I'm interested in him is for his work, La Nuova Scientia, and this was a book on ballistic theory. So this, here I'm showing the title page, and it's actually, you can't see all the detail in it. It's really has a lot of information in it. And at the beginning, it has the little inscription at the bottom in translation tells you that this is very much going to be a book about mathematics. It says, the mathematical sciences speak. Who wishes to know the various causes of things, learn about us. The way is open to us all. And down at the bottom of that diagram, you can see Euclid, and he's letting people in to this courtyard for where they're going to learn their mathematics. And in fact, Tartaglia himself is sort of present in the background of the frontispiece. But more interestingly, is we can see there are two examples of cannon shot. So we can see one where it's going up in the air, and then one where it's going along the ground. So to give us a real idea of what this book is going to be about. So we can see from this diagram, that actually there's clearly an idea that the shot has got some sort of curved trajectory. So what does Tartaglia do? Well, his analysis of the motion is 3 parts. He said, well, okay, you fire your cannon, and it's going to go in a straight line, then it's going to have a curved bit, and then it's going to drop. Now, again, that isn't exactly what he would have seen, but it was sort of much closer than obviously just going straight up and straight down. And for the curved bit, he used just bit of an arc of a circle. So to use the kind of most simplest curve that he could to describe the motion. And so there's the 2 bits. There's the violent motion, which is the bit that goes straight up, and the curved bit, and then there's the natural motion when it's just dropping straight down. Also, what Tartaglia does is he says that he claims the maximum range is going to be when your cannon is at 45 degrees. And that's probably intuitively not such a bad guess if you think about what happens if it goes straight up or it goes straight along. But as we'll see, it doesn't turn out to be quite right. So who's next up? Well, one of the giants, of course, of mathematics and science, Galileo. We know Galileo read Tartaglia, and in his book, The Dialogue of Two New Sciences, which was published in 1638, he includes an inclined plane experiment which determines the path in order to determine the path of a projectile. So what was this experiment? So he says, okay, well, if we have an inclined plane and we put it on a table and we have a kind of curved bit at the bottom of it and we put an inked bronze ball and we let it run down this plane, comes off to the bottom, so it comes off sort of horizontally, and then eventually, obviously, it will drop down and drop onto the floor, and you mark, the ink will allow you to see where it marks on the floor. And so this accelerator ball, it comes down over the tabletop, and it allowed Galileo to work out how far the ball had travelled, both vertically and horizontally. So he divided the motion into these two components. And by doing various experiments, varying the height of the table and the angle of the inclined plane and so on, he had a number of results from which he was able to determine, in fact, that the path would be of such a projectile would be a parabola. And we see here, this is a sketch from one of his notebooks. Now, of course, one of the things that is not being taken into account here is air resistance. And Galileo recognized that, he knew that. So he knew that actually this was very much an idealized solution, having a parabola as the solution. And I've shown on the slide here, this is from the Two New Sciences, but a translation from 1730. I always think it's sort of nicer in some ways to have a translation of as near a time as possible to sort of give you a flavour of the sort of language people were using in the 18th century, rather than if I put it into modern language. So we say the excessive impetus of projects, so that's a projectile, so excessive, so it's going out fast from the cannon, and when it's thrown with such violence may cause some irregularity in the path of the project by making the parabolic lines less inclined or curved at its beginning. But this can be little or no prejudice to our author in practical operations, among the chief of which is the composition of a table of ranges, which contain the distances that balls can travel. So that's what you want to know. If you're firing your cannon, you want to know, well, if you put it at this angle and you've got this size cannonball, where is it going to land? And if you have a table that will tell you that, that's very helpful. And he said, well, that if you've got such a table, but then it tells you for different elevations and so on, but because such projections or shots are made with mortars by help of a small quantity of powder, and these, the impetus not being supernatural, i.e. not being having very large initial velocity, the projects describe their paths exactly enough. So he says, well, if you've got a big enough cannonball, and its initial velocity is slow enough, then it is going to be pretty well parabolic, and you kind of that's a good enough approximation. So he knows that air resistance needs to be taken into account, but he can't actually do it. And we see that even after Galileo, people are still persisting with the three-part motion of Tartaglia, and this is from the Mariner's magazine of 1669, because again, this was a sufficiently good approximation for what people could see happening. It was good enough for them to be able to work out what they wanted to do, because also they realized that incorporating air resistance was a very tough problem. But there were people who incorporated Galileo's ideas, and one of the most popular and most influential was a French text, The Art of Throwing Bombs, 1669, Nicolas Blondel. And you can see it here. These are pictures taken from the book, and you can see the sort of Tartaglia influence, and actually you probably won't be able to read it, but actually you can see the name Tartaglia is at the bottom there of the top picture. So you can see the 45-degree angle is still being considered as optimum. But then you see later on in the book, you see these parabolas where Blondel is discussing what Galileo is doing. So, but then things change quite dramatically. because we have Benjamin Robbins. Benjamin Robbins was a mathematician engineer, British, and one of the sort of quotes I found about him was, it said, he transformed ballistics into a Newtonian science. And Robbins was born in Bath. We don't know much about his early education at all. What we know is that he comes to London when he's about 18, I think, and he goes to study with Henry Pemberton. And this is quite key because Pemberton was the person who was the editor of the 3rd edition of Newton's Principia. And he's doing that work at the time that Robbins is with him. And what we find in Robbins's work is a great influence of Newton's work. So we see influence of Newton's work on part of projectiles moving through resistance, plus we see the use of the calculus. And we see this in Robbins's work, then coming through in 1742 in his text Principles of Gunnery. And as a result of that work, he was awarded the Royal Society Copley Medal in 1746. He was shortly afterwards appointed as the chief engineer of the East India Company and went out to India with various projects, building forts and doing things. But unfortunately, he contracted a fever quite soon after his arrival and died within a year. But his text, as I hope to convince you, was really very influential for the next, for people after him. So why was it? What did Robbins do? So this is quite a short book for the period. It was about 150 pages. And he concentrates on two things, really. On the interior ballistics, that's what's going on inside the gun. So when you fire your shot, your bullet or your cannon, you want to know what is happening inside the gun as it moves through the gun, and then what the initial velocity is going to be as it comes out of the gun. And then the exterior ballistics is what happens then when it's in the air. What sort of path is it going to take? How high is it going to go? What's its range? And so on. And this book has been described as a beautiful example of the scientific method because the way Robbins sets it out is he gives you a series of propositions, and this forms a sort of model for ballistic theory, or for the sort of the physics of a gun, if you like, and then he tests his model against the experiments. And it's quite clear that he recognised the need to understand air resistance. And I think this example shows it really nicely. He takes a particular size shot at a particular angle of a cannon, and he says, okay, if I fire my cannon with this shot, then according to the theory, it should have a range of 17 miles. In fact, if I fire my cannon, its range is something less than half a mile. So there's a bit of a problem. And of course, the problem is air resistance. But I think that is really shows it quite dramatically. What are the things that Robbins most famous for, best known for in ballistics? One of them is his ballistics pendulum. So this, his pendulum, he used Newton's theories, Newton's mechanics and Huygens' theory of the pendulum, and he used it to calculate the initial velocity of the projectile, and also to measure air resistance. So how did it work? Well, I should say there's a nice quote there also from Euler just to kind of emphasize the significance of this particular piece of equipment. Euler says, Robbins' method of finding the velocity of a ball by experiment is without doubt one of the most ingenious and useful discoveries in artillery. Whatever had been delivered on that subject before him was not only uncertain, but erroneous. So how did it work? Well, what Robbins said, the pendulum is the bit hanging down and then the sort of rectangular board towards the bottom, and he fired horizontally at the board, and then the board swung back, and there was a tape that ran through that was connected to the board, and as the board ran back, so the tape ran through the bottom there, and he could then measure the tape. And so the tape would tell him how far the pendulum had swung back. And so he could work out what the height of the pendulum had been, how far it had gone, the arc length to compute this vertical distance through which it had gone, and so compute the gravitational potential energy. So it was a really kind of neat idea and very successful. He also had another piece of equipment, the Robbins whirling arm. This wasn't actually in the book. He came up with this later. And this was to measure air resistance and to try and understand air resistance. So you have this arm sort of whirling around, and he put on different shaped objects onto the arm to see what sort of speed they went, depending on what the shape of the object was, did it affect the speed going around the arm. And he found that the shape of the object indeed did matter, so that it wasn't a question of how much area was going through the airstream, but actually it was the shape as well as the area. And that from this, he could see that Newton's theories were just simply not adequate to describe this kind of complex relationship between the drag and the shape and the orientation as well of the object and the air velocity. And of course, what was subsequently discovered, and maybe we might hear a bit about this in the next two lectures, that there's a real issue about what happens at the boundary. So it's the boundary layer. So what's happening when something goes through the air? What happens to the air at the boundary? And Robbins recognized this, but he didn't articulate it in that way. But what he realized was that the shape and the orientation of the object mattered as far as air resistance was concerned. And so successful was this instrument that it was continued on in use well into the 19th century, and was really just it was only with the advent of wind tunnels towards the end of the 19th century that it kind of went out of use, when wind tunnels were where the people working in aeronautics and were looking at the way objects were affected by wind as it went through the tunnel, so they could have scale. They could scale down. So rather than having an aeroplane going in the air, you could have a model and see what happened. So really, I just want to emphasize here that the fact that this lasted for so long gives you an idea of its significance. And Robbins, again, this is just another quote from him where he says, the greatest part of authors have established that air resistance is in the duplicate proportion of its velocity, but he'll show that this is in fact excessively erroneous, except when confined within certain limits. So he kind of worked out, well, you could use that, you could use the square of the velocity, but it was only valid within very particular circumstances. One of the other things Robbins does is he identifies the Magnus effect well before Magnus. And in fact, sometimes it is now even called the Robbins-Magnus effect. And that is because he observed that sometimes when bullets came out of a gun, they didn't come out straight. They would either kind of veer off to the left or the right. And he wanted to kind of understand why that should be. And he realized that it was to do with the way what was going on with the rifling of the gun and the air that was behind the bullet as it came out of the gun. But this wasn't formally identified until Magnus in the middle of the 19th century. So now, at last, we get on to Euler. I'm sure many of you will know a lot more about Euler than I do, and certainly if Robin Wilson was here, he'd be able to agree with that. So Euler, one of the greatest mathematicians of all time, his work straddles the 18th century, and if we divide his career up into periods, we have him being, when he's born and educated in Basel, he goes off to St. Petersburg, then he gets called to Berlin by Frederick the Great, then he goes back to St. Petersburg. He works he has his finger in just about every single mathematical pie you can imagine, and including ballistics. And he does his main ballistics work when he's in Berlin. So what are his ballistics works? Well, there are three, but really I'm only going to concentrate on the middle one. But the first one is interesting because although he's in St. Petersburg when he does the first one, it's really of interest to historians now and mathematicians now, not because of actually the mathematics in it, but because it's the first paper in which Euler uses the word E to describe the natural logarithms. So just to show you this. And it wasn't published until 1862, so it doesn't really affect the ballistic story at all in that respect. And Euler doesn't publish E as... it doesn't appear in one of his publications, I think, until 1736, but he uses it in correspondence and things. But we know that he was using it in around 1727, 1728, because of this paper that was found after he died and published later. So getting on to the main text, so what prompted Euler to do this work was Frederick the Great. We're in the period of the Wars of the Austrian Succession, and Frederick the Great is he's brought Euler to Berlin. He wants Euler to help him improve things as far as his military might is concerned, and says to Euler, well, you know, I want you to do this work on ballistics and so on. And Euler rather wisely says to him, well, you know what, yes, okay, I could do a whole bunch of experiments, but it's going to take a hell of a long time. And actually, a much better, a more efficient way of dealing with this would be if I used Robbins's book as a basis and worked from that. Because Robbins has done the experiments, and I can use his work and I can amplify it. And he says, what I need to do, obviously, is that he needs to translate it. And that's exactly what he does. So we get his book, the Neue Grundsatz der Artillerie. We know Euler received advice from Johann Bernoulli about it, and also from Field Marshal Count Samuel von Schmettau. It was written in German, which was relatively unusual for Euler, and it's been suggested that was to make it accessible to the lower sort of echelons of the military. Now, if you look at some of the mathematics in it, you think that's a bit of a stretch. But there is a lot of text in it as well, and some of that text, I think, that is quite a kind of feasible conjecture to make when he's being more discursive. One of the main points about it is it's 5 times longer than Robbins's original text. And there's also another sort of rather interesting element to this Robbins-Euler relationship, which is that prior to Euler translating Robbins had a real go at Euler. In 1739, he'd written a paper criticizing his Mechanica, and in no uncertain terms, if you read it, you can see, I mean, he's really very unsparing in his criticism and the kind of language that he uses. So I've just given a couple of examples here. He says, well, Euler's unfortunately followed the principles of his calculus with so little caution as even to contradict Euclid himself. And then another place, the 4th chapter has affixed to it a very pompous title. And I mean, it's full of this sort of language. Euler, but nonetheless, that hasn't prevented Euler from recognizing that Robbins has done some, Robbins's book is very important. And I gave you an example of him praising Robbins with the Ballistics Pendulum, but he also doesn't hold back on criticizing him either. He says, Robbins's account appears to be so well grounded and conformable to the truth as not to admit of the least objection, but he must be either unacquainted with several books on the theory of artillery, or else he must have purposely passed over them in silence in order to exalt the merit of his own discoveries. So he's using this as an opportunity. He's having his own little dig at Robbins. So what is in Euler's book? One of the things we see right in the preface is Euler endorsing the use of fluxions for artillery purposes. And so this... So here we see him being very explicit about this. Some are of the opinion that fluxions are applicable only in such subtle speculations and can be of no practical use, or at most whatever conclusions can be obtained by them are owing to the well-known lower parts of mathematics. But what has just been said of artillery is sufficient to remove this prejudice. It may be affirmed that many things which depend on mathematics cannot be explained in all their circumstances without the help of fluxions. So this is actually using Newtonian language here for the calculus. So he's endorsing Robbins's Newtonian approach to ballistics. He also makes it clear that finding the true path of a cannonball is no trivial matter. He says, here again, Mr. Robbins gives us further expectations of discovering the real track of a cannonball. It is some years since his book was published, and nothing more that I know of has appeared on the subject. The inquiry is so difficult that the author was in the right to require a longer time to complete it. So he acknowledges here that Robbins's work isn't complete, and Robbins himself recognised that there was more work to be done. So how does he expand it into sort of 750 pages? Well, basically, he goes through Robbins's text, he takes each of Robbins's principles, and he examines them closely and builds his own principles on them. So he will either, he might question some of Robbins's assumptions, he might point out errors, he will add new material. And so, for example, he thought that Robbins's theory of determining the velocity of the cannonball leaving the gun wasn't very accurate, because Robbins didn't actually consider the length of the gun. So you can imagine that if you have a gun and it's sort of this long and you've got your sort of cannonball here or whatever, it's only got to go there, compared to if it's here, and what's going on, the internal ballistics of what's going on. I mean, the length of the gun is clearly something that needs to be taken into account. And something else he pointed out was the fact that Robbins, in the ballistics pendulum, he assumed that when he fired at the pendulum, it would always hit the center of gravity of the pendulum board. And Euler says, well, the likelihood of that happening is pretty small, and you need to take account of that. And actually, Robbins himself had realized that he needed to do that and had presented a paper to the Royal Society explaining that, but it hadn't gotten incorporated into the book, and Euler hadn't seen it. Euler also investigates several new topics, particularly the theoretical strength of a gun barrel. So you can imagine, I mean, you have your cannon and you've got your cannonball. Well, you don't want, when you fire it, for the cannon to explode. You want the cannonball to go out of the end and go and do what you want it to do. So this is really what's considered like an early analysis of a pressure vessel. So he really looks at that, something Robbins hadn't done. He examines things like metal for a gun barrel. He looks at the structure of the gun barrel, the gun carriage, what happens with the recoil, and he also even looks at quality of gunpowder and how that can affect what goes on in the interior ballistics. So a little bit of the mathematics. So this is a diagram from his book, and so Euler is looking at what happens with just horizontal fire. And he says, well, if we have a ball fired horizontally from E to F, and he's just looking at quite a short distance, and he says the ball falls to G. So we were interested in this distance E to F, although the ball is actually following this trajectory, so it's coming down a bit, so it's landing down at G. And he says if we look at some point, we take just some point on this line EF, say P, by the time the ball has gone that distance, it will have dropped down a bit to M. And what Euler wants to know is, well, how long is it going to take for the ball to reach P? What angle has the ball gone through in order for when it reaches M? And what's the velocity when it gets to P? And he does quite a lot of mathematical analysis goes on, and he does something. He says, no, this isn't quite good enough. I need to make a different assumption here, and he kind of works it through all again. And I'm just putting this up here just to show you the kinds of mathematics that he's dealing with, and to kind of make the point that I think probably the lower military echelons probably wouldn't have been handling this too well. But we can see the kind of beginning of a series going on here, x squared, x cubed, this is for the time, and so on. And the things that he needs to take into account, things like the diameter of the ball and what assumptions you make about the density of the ball and the density of the air, and so on. He looks at what happens, the most natural thing, the oblique shot. So when you're firing at an oblique angle to the horizon, and again, I just want to show what eventually comes out at the end of his analysis. So he shows y is the height of the maximum height of the trajectory, the height of the trajectory rather, as you go round, and then EF, of course, is the range. So overall, what are Euler's results? So he says, well, the range at any given angle of elevation will be less than that of the case with no air resistance. So if you've got air resistance, you'll get a lower range, which we, of course, would expect. But also, as the angle changes, then you're going to get change in between that range and the range in the non-resistance case. And Euler says, actually, what's going to happen is the angle for maximum range is going to be less than 45 degrees. And providing you've got quite a heavy shot moving at a slow speed, then you can get an estimate for the angle of that will give you the maximum range. But it turns out, as he says, well, in fact, this is not very useful, and improvements will have to wait for a later date. He also incorrectly denies the existence of the Magnus effect. He thought it was to do with the actual bullets themselves, and there were imperfections in the shape of the bullet, and that was what would cause the bullet to spin off in different directions. Interestingly, he also expresses D'Alembert's paradox, which is 7 years before D'Alembert. That's the paradox where you have an inviscid, incompressible fluid, and you've got a body moving through the fluid in constant velocity, and the theory tells you that there's no drag on the object. Well, actually, practice tells us that there is, and again, it's back to the boundary layer problem. But Euler has this before D'Alembert. The paper that where he does manage to get rather more results is published in French. He says researches in the true curve, which describes the body thrown into the air or in some passing through some arbitrary fluid. And this is where he really does give a full analysis of the equations for ballistic motion within a resisting medium. So not just air, as it were, but a resisting medium in general. He does assume that it's proportional to the velocity, the air resistance was proportional to velocity squared, so he's still working within a very narrow range. He numerically integrates his equations for the trajectories range, altitude, time, and velocity, and he provides ballistics tables, which of course are what Frederick really wanted. In fact, Robbins didn't provide ballistics tables initially with his book, but he does later in 1746. But Euler didn't know about those, and because they weren't published until 1761, until after Robbins dies. What about the influence of Euler? Well, one of the things we see here is a letter from Turgot to Louis XVI. And Turgot was the minister of Louis XVI's Minister of the Navy and Controller General of the Finances, and he tells Louis XVI, look, actually, what we need are these two books of Euler's. One will be very useful for the Navy. This is on the treatise on the construction and manoeuvring of vessels, and the other is his treatise on artillery. Now, the naval treatise was written in French anyway. But of course, Euler's artillery treatise was written in German, so he needed to get it translated. But also, it's kind of quite an interesting point here, where he's sort of saying, well, of course, we really shouldn't make an edition without consulting the author, because that's sort of not, that might sort of be, that's not quite right. But it's easy to recompense him in a manner very flattering for him and glorious to your majesty. So as long as, the king gives him authority to do this and also gives him the money to do it, he will sort it out. And he says this sum will be paid from the secret accounts of the Navy. And then we get Turgot writing to Euler, and he says, when I was in charge of the Navy, I thought there was nothing better I could do than get them to study your two books. And of course, I got the King's permission to print the original one in French, the naval one, but the other one I needed to translate. And of course, had I been able to get in touch with you, I would have asked your permission. But anyway, but I knew the king would compensate you, and so here it is. Here's 1,000 rubles as evidence of his esteem for your work. And then we get, shortly afterwards, we get an edition in English. So we've got Robbins in English, going to Euler in German, coming back to English again. So it's Euler being translated into English with Robbins's text in it again. So, and Hugh Brown was at the Tower of London. He was connected with the Board of Ordnance. They commissioned him to translate Euler back into English. Notice that here Hugh Brown, instead of both Euler and Robbins, talked about the new principles, but Brown, for some reason, talks about the true principles. Sort of a translational nicety. We get the French translation of Euler is by Jean-Louis Lombard, who was professor of mathematics at the Royal School of Artillery at Auxon. And he was a teacher of Napoleon. And we have evidence of the fact that Napoleon used this work. We know that he studied Lombard's translation when he was at Auxon. And also, he himself, Napoleon, wrote a 12-page summary of Robbins. And it's in the Napoleon archive. Was published unedited in 1895. So I've seen the published version. I haven't seen the Napoleon manuscript because it would be very nice to be able to show you a picture of that. But so we absolutely know for sure that Napoleon used Euler and used Robbins and was very impressed by them. So in summary, we can see the kind of spread of Robbins and Euler's work on ballistics. We also know that in 1751, that Robbins's text was translated into French back then, but just in a manuscript form for the French Academy of Sciences. Then we get 1761, we get James Wilson publishes all of Robbins's works after Robbins has died. So he republishes the new principles. Then Gravenitz, a German infantry officer, provides a complete set of ballistics tables using methods from Euler's text. Tempelhof, who was the director of the Prussian Military Academy, wrote a book built completely on Robbins and Euler's analysis. I've shown you Lombard's text, which was studied by Napoleon. And then we also have the Hutton text, which was in 1805. Charles Hutton edited a new edition of Robbins's collected works for use at the Royal Military Academy in Woolwich. So we see it really dispersing out from Robbins originally in England. It goes to Euler into German, then back from Euler back into English in 1777 with Hugh Brown, but then also into French with Lombard. And so I've got it's my final slide as a sort of summary of how these texts dispersed throughout England, France, and Germany at really a very kind of critical time, and of course a period where there were wars going on all the time. And that was, we really probably need to have somebody talking about what happens next, because there's a bit of a jump to World War I. But anyway, I hope that's given you an idea of some of the problems, particularly trying to understand both the internal and external ballistics. These were not trivial problems, and were recognized as such in the 18th century. And really, the whole science of ballistics was given a huge boost by the work of both Robbins and Euler. So thank you very much.